Alright, today we're talking about 6.4, which is parametric equations. And a parametric equation is just an equation that depends on what we call a parameter or another number. So for instance, these x equals cosine t and y equals sine t, those are parametric equations because they depend on t. And t is just any real number. In this particular case, t within cosine and sine would have to be in radians because it's a real number that we plug into a trig function, so a radian. So those x equals cosine t, y equals sine t are the parametric equations, and t is the parameter. What we're going to be doing is we're just going to be rewriting these parametric equations, and when we do that, we call that eliminating the parameter. So we're going to eliminate the parameter and then graph it. So how we start these is, well, we got this system of equations here, x and y equal 3 cosine t and 2 sine t. We're going to start by writing these as the trig function equals everything else. So we're going to isolate the trig function. So on 1, we get cosine t is equal to x over 3, and sine of t equals y over 2. Now with those, I'm going to use one of my Pythagorean identities. If you look on your formula sheet, you'll notice, hey, I have a Pythagorean identity that involves cosine and sine. It's cosine squared of t plus sine squared of t equals 1. That's my pretty standard Pythagorean identity. Now I'm going to plug these x over 3 and y over 2. I'm going to plug those in for cosine and sine in that Pythagorean identity. Well, when I do that, I end up getting x over 3 all squared plus y over 2 all squared equals 1. And now I'm going to simplify that as far as possible. I get x squared over 9. Ooh, that's not a very good square. Let's rewrite that. X squared over 9 plus y squared over 4 equals 1. What I just did there is I eliminated the parameter. And that boxed equation is what I need to write to get full credit for when I ask you to eliminate the parameter. The next part of graphing it is probably new to most of us. We might have seen it in an algebra class, maybe geometry. However, we're going to give a bit of a crash course in drawing these eliminated parameter equations. Now there's two types of equations or graphs we're going to see today, and that's ellipses and hyperbolas. An ellipse is like a football. It's an oval. And it's what happens when we have a plus in the middle here. When we have an x squared over a number plus a y squared over a number equals 1, that is an ellipse. And how I draw that is I start by looking at my x. I should probably let's give the general formula first. This might look kind of familiar to a circle. A circle is x minus h squared plus y minus k squared equals 1. This time we're dividing by these a squareds and b squareds. And how I draw this is I look at my first term, the x squared term. And I think, hey, am I subtracting anything from x? No. Then I look at the y term. And am I subtracting anything from y? No. So that means my center, the center of my ellipse, is at 0, 0. So if we come back to my general equation, the center is at the point hk. In this case, I'm not subtracting anything from x or y, so my center is at 0, 0. Then I look at the number in the denominator. For x, it's 9. If we look at my general formula, it's all divided by a squared. And I'm going to be going a units to the left and to the right in the positive and negative x direction because I'm dividing it by x. Since my number divided by x is 9, I'm going 3 units to the left and to the right. Make some points. And then I look at the y term here, y squared over 4. I'm going to go b units, right? I'm dividing by b squared, so I'm going to go b units to the up and down. So I look at here, I had a 4, so I'm going to go 2 units up and 2 units down. And then I just connect those dots I just made. And that is my ellipse. We'll see another one here in just a second. Same idea. I'm going to start by isolating my trig function in both of them. So I got sine of t, not sine squared, equals x minus 3, and cosine of t equals y plus 2. And I'm going to use the same Pythagorean identity. Sine squared plus cosine squared equals 1. Alright, plug that in. I end up getting x minus 3 squared plus y plus 2 squared equals 1. Again, I just plugged it into my Pythagorean identity. Sine squared of theta plus cosine squared of theta equals 1. So I end up getting this boxed function, and that is my equation that's the equation you need to give to get full credit when I ask you to eliminate the parameter. We can think of these as all over 1 if we want. We don't need to place the 1 there, it's unnecessary. However, how do I draw this thing? If we go back to my original equation for the ellipse, it's x minus h quantity squared over a squared plus y minus k quantity squared all over b squared equals 1. So first order business is, what's my center? Well, remember my center is, in this case, hk. Remember the signs are backwards. X minus h, y minus k. So my center in this case is going to be, well, it's x minus 3, so my x coordinate is 3. Y plus 2, so my y coordinate is in minus 2. They're backward signs. So let's plot that. 1, 2, 3, 1, 2. That's my center. Then I think, hey, how far am I going left and right? How far am I going up and down? Well, in this case, it's divided by a squared. I go a units to the left and to the right. Since I'm dividing by 1, the square root of 1 is just 1. So I'm going a units, or 1 unit to the left and to the right. Same thing for y. 1 unit up, 1 unit down. So this time it's a circle. Very small circle. And that's the graph of this equation. Remember, my order of operations here, if you want to think of it in terms of that, is isolate the trig functions, plug them into a Pythagorean identity. We're going to use a different one in just a second. And then lastly, plot it. Plot the center, figure out how far you go left and right. So for this last one, we're using secants and tangents. The operations here, how we're doing things, the order of which we do things will not change. First, I isolate the trig function. Well, in this case, I get secant of t is equal to x minus 3, all divided by 2. And I get tangent of t is equal to y minus 2, all divided by 4. Now I need to think, is there a Pythagorean identity that involves secant and tangent? Well, if you go back and look at your formula sheet here, we have one that says, hey, I got the, don't need that little mark, I get the tangent of theta plus 1 is equal to secant of theta. Sorry, that should be tangent squared, my apologies, equals secant squared of theta. That's on your formula sheet. Now I need to do a little rearranging here. I'm going to get the 1 by itself, so I get that 1 is equal to secant squared of theta minus tangent squared of theta. And now I'm going to plug everything in. I'm going to plug my secant in, my tangent in. So I get secant squared, so I just plug x minus 3 over 2 all squared. Minus, this is where we're different, we're minusing the tangent here. Y minus 2 all divided by 4 squared equals 1. Now I need to do a little simplification here. I get x minus 3 quantity squared all divided by 4 minus y minus 2 quantity squared all divided by 16 equals 1. So this boxed equation is what I need to give if I ask you to eliminate the parameter. Drawing it's a little more tricky. Notice before we had an ellipse and a circle because we added the two terms. This time we're subtracting. When we subtract the two terms, that means we are going to get a hyperbola. Now if we don't remember what a hyperbola is, we'll go over a quick crash course of that, but we'll do a lot more examples in class to freshen your memory or to teach you to begin with. So what I start with is I start by plotting my center again. Well, what am I subtracting x by 3? What am I subtracting y by 2? So my center is 3, 2. That's not different. Again, I'm going to see how far am I going left and right, up and down. Well, left and right, I'm dividing by 4, so I go 2 units to the left, 2 units to the right. How far am I going up and down? Well, I divide by y by 16, so I go 4 units up. 1, 2, 3, 4. 4 units down. 1, 2, 3, 4. Now, normally, if we were doing an ellipse, we'd connect those dots with an oval. We're doing a hyperbola here, though, because we're subtracting these. So my first order of business here is I'm going to make a box with these points that I just drew. Alright, and with this box, I'm going to make my diagonals. I'm going to extend them out. Make these diagonals. Those are my asymptotes. Those are the lines that my graph is not going to cross. Okay. Now with a hyperbola, my graph is either going to open up to the left and to the right, or it's going to be opening up and it's going to be opening down. Now to figure out which one it is, I have to go back to my equation. What term is first? Well, my x term is first. It's an x term minus a y term. So because x is first, and x goes left and right, my hyperbola is going to be opening to the left and to the right. So I'm going to start with the point that I drew on my box, the left point and the right point. And now I'm just going to open it up with a parabolic motion to the left, approaching my asymptote. So it's going to look something like this. To the left and to the right. And that red curve is my graph. So again, to recap, same process. Isolate the trig functions, substitute it in using a Pythagorean identity, and then simplify as far as possible. That was eliminating the parameter. To draw it, since I'm subtracting this term here, I first draw out my center. That's nothing new. Then I draw out my points up and down, see how far I go. But the only difference is because I'm subtracting here, I make my box. I connect it with a nice purple box there. And then I draw on my diagonals. Then I have to go back to my equation and think, hey, the x term is first. Order matters in subtraction. Since my x term is first, I open up my hyperbola or my parabolas left and right instead of up and down. So go ahead and write your summary. You guys got a lot to write about. I would imagine you'd have some questions probably about ellipses and hyperbolas and all that fun jazz. And then take a look at your assignment before tomorrow.